In this video, we will be reviewing the concept of frequency. The main aim of reviewing this concept of frequency is that we want to move from continuous time signal to discrete time signal. As you can recall from the previous video that this signal which I have drawn on the left is a continuous time signal and this is xn, that is discrete time signal. Okay, so this continuous time signal is defined for the continuum values of time axis, and this discrete time signal is defined only for certain instants. It is undefined for these values in between the instants. It is defined at 0, 1, 2, 3, 4, etc. Okay. So in the layman's way, we can say the concept of frequency as frequency can be said as the inverse of time. It is the inverse of time. But let's see the first case, that is continuous time. We can represent a continuous time sinusoidal signal as an analog signal xat is equal to a cos omega t plus theta. We have used this subscript a to denote the analog. Analog is the meaning that this is also continuous in the amplitude domain also. The time axis is also continuous and amplitude is also continuous. So this is analog signal xat is equal to a cos omega t plus theta, and this is defined for every value of t, that is minus infinity to infinity, where a is the amplitude, omega is the angular frequency in radians per second, t is equal to time in seconds, and theta is the phase in radian. If we can write this angular frequency in terms of the frequency as 2 pi f, where f is in cycles per second, then we can use these two equations to make up this relation. Xat is equal to a cos 2 pi ft plus theta, where f is the continuous time frequency. Okay, this is the continuous time frequency. So this continuous time frequency can range from minus infinity to infinity, as we will see in next. So this is the overall definition of a continuous time sinusoid which exists for all time. Let's visualize it, what we are trying to say. The sinusoid looks like this. Okay. So this is the time period of the sinusoid, and when we say the frequency f, so the frequency is the notion that we are trying to say that how many cycles per second, how many cycles per second it is executing. Let's say this is 1 second. This is 1 second in the time axis. So we can see that this completes first cycle here. This is first cycle and this is second cycle. So this is completing 2 cycles per second. So f is equal to 2 cycles per second or 2 hertz. Okay, which implies that the angular frequency will be 2 pi. F is equal to 2 into pi into 2 is equal to 4 pi radians per second. So like this we can find out the angular frequency of any signal. This is the angular frequency. Properties of continuous time sinusoid. For every fixed value of f, xat is periodic with Tp is equal to 1 by f. we started here from this very basic notion that f is equal to 1 by t, that is frequency is the inverse of time. So we can write inverse also, that time is the inverse of frequency, which leads to xat plus tp is equal to xat. That is, any advancement, any lag in the original continuous time sinusoid, any advancement in the original continuous time sinusoid by an amount of the time period will lead to the same sinusoid. So I can write this relation as like this also, xat plus minus tp is equal to xat. And to satisfy this constraint, continuous time sinusoid becomes everlasting signal. It exists for all time. Increasing the frequency f results in an increase in the rate of oscillations of the signal, in the sense that more periods are included in a given time interval. Let's say in this above diagram, if I include one more signal, this is one more signal. It executes 4 periods in the 1 second period. So it is having 4 cycles per second. So it is having higher frequency. This statement says this. Increasing the frequency, f results in an increase in the rate of oscillation of the signal, in the sense that more periods are included in the given time interval. And what was the second property? Second property says that continuous time sinusoidal signals with distinct frequencies are themselves distinct. So whenever I will change this f value, I will get a new sinusoid in the continuous time case. Frequency range of continuous time sinusoids, because every sinusoid having a different frequency will be distinct. That's why the frequency range is from minus infinity to infinity, which implies that the angular frequency will also range from minus infinity to infinity. Now we will consider the case of discrete time sinusoid. A discrete time sinusoid, which depends on the instant n, can be written as xn is equal to a cos omega n plus theta, where n ranges from minus infinity to infinity, where omega is the frequency in radians per sample. Note that here we are having radians per sample, and on the continuous time side we were having radians per second, because the time axis was in seconds here in this continuous time case, and in this case the time axis was instants or samples. This is the n is the sample number. Okay, that's why we are having radians per sample, and theta is the phase in radians as in the continuous time sinusoid case. Also here this omega becomes 2 pi f. It becomes 2 pi f, where f is the frequency in cycles per sample. There we had cycles per second in continuous time case. Here we have cycles per sample. As in the case of continuous time sinusoid, we use this relation to arrive at the new formulation. So this is the formulation for discrete time sinusoid. Xn is equal to a cos 2 pi fn plus theta. So f is the frequency in discrete domain. Now we will see the properties of discrete time sinusoid. A discrete time sinusoid is periodic only if its frequency f is a rational number. That is, f can be expressed in the form of p by q. F can be expressed in the form of p by q, implies that a cos 2 pi fn plus theta is periodic, otherwise signal is said to be aperiodic. Whenever we see f irrational, we can straight away say that the signal cannot be periodic, so it will be discrete time aperiodic signal. In the case of discrete time only. In the case of continuous time, we are not restricted by this constraint. So this is the proof. Periodicity requires xn is equal to xn plus n for all n, where n is said to be the period in discrete domain. N is the samples. Actually, it can be seen as samples. We can say that xn is having periodicity of 7 samples. So it will repeat its pattern after 7 samples. So n is equal to 7, which implies n is equal to 7. So we can write this relation. We have excluded this a from here because a can be taken as 1. Cos 2 pi fn plus theta is equal to cos 2 pi fn plus n plus theta. This can be expanded. Cos 2 pi fn plus 2 pi fn plus theta. We know that cos 2 pi k plus r is equal to cos pi r. This is the basic relation for cosine signal, that any integral multiple of 2 pi is added to r, which it leads to the signal itself. The above relation holds only if 2 pi fn is equal to 2 pi k, because it should be an integral multiple of 2 pi k. Then only it will be equated to this. So this implies that we solve it. 2 pi gets cancelled. F is equal to k by n. That is the rational number, which was our case earlier. This was the case we were trying to prove, p by q. So it is a rational number k by n. Note that n is the periodicity of the discrete time signal. Let's go to the second property of the discrete time sinusoid. The second property says that discrete time sinusoids whose frequencies are separated by an integral multiple of 2 pi are identical. It means if I have given xn is equal to cos 0.1 pi n, it is identical to cos 2.1 pi n, that is cos 2 pi n plus 0.1 pi n. I add a integral multiple of n, or let's say I can add 2 pi k plus 0.1 pi n. I will get the same sinusoid. How can we write it in generalized term? xkn is equal to a cos omega kn plus theta, where omega k, that is the frequency in digital domain, discrete domain. The frequency in discrete domain, omega k is equal to omega naught plus 2 pi k. This was the case. Here we had omega naught is equal to 0.1 pi n, and this is 2 pi k plus 0.1 pi n. So omega naught should be in the interval of minus pi to pi. So we generally restrict our omega to minus pi to pi. So this statement says all sequences xkn for which a cos omega kn plus theta, where omega k is omega naught plus 2 pi k. This statement says, let's say I had omega naught is equal to 0.1 pi n. I can add anything 0.1 plus 2 pi or 0.1 plus 4 pi, 0.1 plus 6 pi. These all sinusoids will lead to the same discrete time sinusoid. The same discrete time sinusoids will be formulated from this omega naught is equal to 0.1 pi n, provided we add the integral multiple of 2 pi. So all the discrete time sinusoids which are separated by an integral multiple of 2 pi are identical. They are indistinguishable. The highest rate of oscillation is achieved in a discrete time sinusoid when omega is equal to pi. or equivalently f is equal to half. This is the result of this second property. We are restricting ourselves in the interval minus pi and pi. So the highest rate of oscillation of the, we can write as omega max is equal to pi, or omega minimum is equal to minus pi. Okay, if we are concerned with the absolute values, we can write omega max is equal to pi and omega minimum is equal to 0 in terms of absolute values. Because if we consider the notion of negative frequencies, this is the range minus pi to pi. And we will see later that this frequency of negative frequencies are the replica on this is I'm trying to say. This is the negative frequencies and this is the positive frequencies. Equivalently, f is equal to half. How we are getting half? F is equal to, we know that 2 pi f is equal to omega. This is the relation for discrete time frequencies. So f is equal to omega by 2 pi. So f max is equal to omega max upon 2 pi. Omega max is, we have written it, pi. Omega max is pi. So this is 2 pi is equal to half. So f max is equal to half, or equivalently f is equal to minus half. This is the frequency at which highest rate of oscillation of discrete time sinusoid is found. So we get the range of discrete time frequencies as half and minus pi to pi. This is our final relation. So what we have seen in this video, we have learned that there is much difference between the continuous time sinusoid and the discrete time sinusoid. The continuous time sinusoid, the distinct continuous time sinusoids are generated whenever we change this f, the frequency value, capital F frequency value. Whenever I will change, I will get distinct sinusoids. But in the case of discrete time sinusoids, changing f may or may not change the discrete time sinusoid. If the change from first sinusoid, let's say it is having f1 frequency, and the second sinusoid is an integral multiple of 2 pi k, 2 pi, that is we are writing the amount as 2 pi k, k is equal to 0, 1, 2, 3 something. So if the difference between the frequencies is an integral multiple of 2 pi, then the two sinusoids are identical, they are indistinguishable. And this will lead to the maximum frequency in digital domain and discrete time domain to be pi, or equivalently f is equal to half. F max is equal to half. F max is equal to half and omega max is equal to pi. And in the case of continuous time signal, continuous time sinusoid, the continuous time frequency is ranging from minus infinity to infinity, as well as the angular frequency is ranging from minus infinity to infinity. That's all for this concept. Thank you.